Hexachlorobenzen, or HCB, is an odorless, chlorinated, hydrophobic organic compound with the chemical formula of C6Cl6. It's a white crystalline solid that is highly soluble in fats, oils, and inorganic solvents. Previously, HCB was used in the production of fireworks, ammunition, rubber, wood, and was also a pesticide. However, due to its harmful effects on human health, HCB use was banned. Because HCB takes in faster than it breaks down, the compound still exists in the environment. HCB sticks to the soil and sediments of the water and then accumulates in plants, fish, birds, as well as other animals. Since the ban, there is no commercial use of HCB. However, the compound still appears as a byproduct of other chlorinated compounds and pesticides like the ones seen on the screen.
HCB is primarily found in soil and barely in water. However, any HCB in drinking water is a big environmental concern. The EPA set an MCL, or maximum contaminant level, of 1 part per billion of HCB. If a person consistently drinks water with a high HCB level or is exposed to contaminated soil, there are several known adverse health effects, including reproductive, liver, and kidney problems, and increased risk of cancer. Since HCB is bioaccumulative and toxic to birds, the contaminated soil affects them as well. When MCL levels are exceeded, remediation is necessary in order to prevent long-term exposure. The HCB can be removed from water using granular activated carbon. When soil is contaminated and is affecting wildlife, the soil needs to be treated and could become a Superfund site.
Via use of the Level 1 Fugacity model, we are able to illustrate how different chemicals react in different environments. While this model is not intended to produce an exact, detailed prognosis of the fate of a given chemical, the model can easily be used to vary the standard scenario to depict an educated prediction. By varying the scenario, we are able to improve the simulation and obtain an enhanced understanding of the behavior of a single molecule. The Fugacity approach is beneficial in its application to evaluate models, laboratory experiments, and fieldwork in an attempt to better understand the mechanisms that regulate environmental distribution and the fate of a chemical under specific conditions. Once these are determined, the model can then be used to define acceptable distributions in a given territory. In addition, it is proposed that by converting dissimilar concentration units related to various media in one common unit, it is fairly easy to evaluate the significance of various concentrations in different environmental locations. By doing so, it becomes easy to depict a trend for bioaccumulation of the chemical at hand. For example, one common conversion is to transfigure all Fugacity results to pascals. In the case of equifugacity, calculations for a medium which highlights the necessary condition for the equilibrium phase, we are more capable of identifying hotspots and clean areas in the said environment.